In this problem, we have a hollow metal sphere, that's this guy, with inner and outer radii of 6 centimeters and 10 centimeters. We have a point charge at the center. So our point charge is right here. It doesn't say anything about the charges on the sphere or the point charge. We know that the surface charge density on the inside surface, so the charge density right here, is minus 100 nanocoulombs per meter squared. And we know that the charge density on the exterior surface, on the outer surface, is plus 100 nanocoulombs per meter squared. So what this is telling us is that there is some charge on the inside surface and there is some charge on the outside surface. The radius here we might call A, and the radius here we might call B. And what we're asked for is what is the electric field here, here, here. So we know from experience electric field depends on charge. So before we get into finding the electric field, why don't we see if we can find the charge on this inner surface, the charge on this outer surface, and then we'll see if we can sort out what is the point charge. So for the inner surface, we know that the charge density eta is equal to the charge on the inner surface divided by the area of the inner surface. So the charge on the inner surface is the density times the area. The area of the inner surface is the area of a sphere. It's 4 pi r squared. So we'll put in our numbers there. Minus 100 times 10 to the minus 9 coulombs per meter squared times 4 times pi times a squared, which is 6 centimeters squared. Put that through the calculator, get a value for our charge, and that turns out to be minus 4.52 times 10 to the minus 9 coulombs. So minus 4.5 nanocoulombs. Let's use the same idea and find the net charge on the outer surface. So on the outer surface, the charge density is the charge on the outer surface divided by the area of the outer surface. So the charge on the outer surface is the charge density times the area. So the density times 4 pi. This time the radius of the outer surface is 10 centimeters. We called that B. We'll plug our numbers in. And when we do that in the calculator, we get for our net charge 1.26 times 10 to the minus 9 coulombs, 1.26 nanocoulombs. Okay, that's the charge on the inner surface, charge on the outer surface. Now let's find the charge, the size of the point charge that's at the center. So for the point charge, this diagram's already pretty full, so let's not mess that up. There's our point charge, here's our metal sphere. What we could do is draw a Gaussian surface inside the metal sphere. Let's draw a Gaussian surface right here, some distance r away, but it's inside the metal sphere. What we know in here is that E equals 0 because E is equal to 0 inside of a conductor. So we'll write down Gauss's law. The net electric flux is the integral of E dot dA equals to the charge inside over epsilon naught. The electric field is 0, so 0 is Q inside over epsilon naught. So the net electric charge inside the Gaussian surface is equal to 0. Okay, what is that net electric charge equal to? There's only two things inside that Gaussian surface that can be charged: the inner surface of the conductor, so Qi, and the point charge. So 0 is the charge on the inner surface plus the point charge. So the point charge is negative of the charge on the inner surface. So it's negative of negative 4.52. So that means it is plus 4.52 nanocoulombs. Now we know all of our charges in our picture. We now know the point charge, the charge on the inner and the outer surface. Now we're set to use Gauss's law to find the electric field at the places we're asked for. We'll do that part next.